According to the National Electrical Code Section 501.15a, flexible metal conduit may be used only for exposed work where flexibility is needed and shall not be used, firstly, where subject to physical damage, and secondly, in hoistees or on moving parts. However, there is an exception. Listed liquid-tight flexible metal conduit, or LCFMC, and liquid-tight flexible non-metallic conduit, or LFNC, shall be permitted for use in hoistees and on moving parts without containing conductors as an equipment grounding conductor and for bonding equipment and enclosures. NEC Section 502.15 states that flexible metal conduit shall be grounded, meaning connected to an equipment grounding conductor or to the grounding pole of a receptacle outlet, and shall be considered grounded if it is connected to a metal outlet box or switch box, or to non-metallic outlet box or switch box provided with a grounding terminal or means for grounding. However, if ground continuity is interrupted, a separate equipment grounding conductor shall be provided. NEC Section 502.25 explains that where the protection of the equipment grounding conductor is required by NEC 501.15b, the flexible metal conduit alone shall not be relied upon to provide such protection. There are a couple of exceptions to this. Firstly, listed liquid-tight flexible metal conduit and flexible metal conduit type FMC may be used as an equipment grounding conductor provided all the following conditions are met. 1. The conduit length between points of grounding does not exceed 6 feet. 2. All connections are made up tight with fittings designed for grounding. 3. The conduit is not subject to physical damage. And 4. The conduit is protected from corrosion. Secondly, other types of flexible metal conduit and fittings specifically listed for grounding shall be permitted for grounding. To answer the question, it is permissible to use flexible metal conduit fished in a metal stud wall within a healthcare facility, specifically nursing home resident rooms, on a 20 amp circuit if the raceway qualifies for an equipment grounding return path in accordance with 250.118. You will need to pull an equipment grounding conductor. The maximum combined length of 6 feet only applies to flex not listed for grounding. To elaborate further, let's delve into the specific requirements and considerations for using flexible metal conduit, or FMC, in healthcare facilities, especially nursing homes, focusing on resident rooms and 20 amp circuits. The primary concern revolves around ensuring a reliable equipment grounding path to protect patients, residents, and staff from electrical hazards. The NEC provides specific guidelines to ensure safety in these sensitive environments. Let's break down the key aspects. Firstly, understanding the types of flexible metal conduit is crucial. The NEC recognizes several types, each with its own characteristics and applications. These include standard FMC, liquid-tight flexible metal conduit, or LFMC, and other specialized types. Standard FMC is typically used in dry locations where flexibility is needed for wiring, but it's not suitable for wet or corrosive environments. LFMC, on the other hand, provides a liquid-tight seal, making it suitable for damp or wet locations where protection from moisture is required. Secondly, grounding requirements are paramount. The NEC mandates that all electrical equipment be properly grounded to provide a low impedance path for fault currents, minimizing the risk of electric shock. For FMC, grounding can be achieved in several ways, depending on the specific installation and the type of conduit used. As we covered earlier, if the FMC is listed for grounding and meets certain conditions, it can serve as the equipment grounding conductor. However, if it's not listed for grounding or if the conditions aren't met, a separate equipment grounding conductor must be installed inside the conduit. Thirdly, the 6-foot rule comes into play when using FMC as an equipment grounding conductor. According to the NEC, if you're relying on FMC itself to provide the grounding path, the combined length of the conduit between grounding points cannot exceed 6 feet. This limitation is intended to ensure that the impedance of the grounding path remains low enough to effectively clear fault current. However, this rule doesn't apply if you are using a separate equipment grounding conductor inside the conduit. Fourthly, healthcare facilities have additional requirements. The NEC has specific requirements for healthcare facilities to minimize electrical hazards to patients. These requirements cover various aspects of electrical installations, including wiring methods, grounding, and the use of isolated power systems in critical care areas. When using FMC in a healthcare facility, it's essential to comply with all applicable requirements to ensure the safety of patients and staff. Fifthly, installation practices are critical. Proper installation is essential for ensuring the effectiveness and safety of any electrical system. When installing FMC, make sure to use fittings that are listed for the purpose and that are properly tightened to provide a secure connection. Avoid kinking or damaging the conduit, as this can compromise its ability to provide a reliable grounding path. Additionally, protect the conduit from physical damage and corrosion, as these can also degrade its performance. Sixthly, inspection and testing are necessary. Once the installation is complete, it's important to inspect and test the system to verify that it meets all applicable requirements. This includes visually inspecting the conduit and fittings to ensure that they are properly installed and that there are no signs of damage or corrosion. It also includes testing the grounding system to verify that it provides a low impedance path for fault currents. If any issues are found, they should be corrected immediately to ensure the safety of the system. So, considering the specific scenario of using FMC in a metal stud wall within a nursing home resident room on a 20 amp circuit, the following considerations apply. Firstly, determine if the FMC is listed for grounding. Check the manufacturer's specifications to see if the conduit is listed as suitable for use as an equipment grounding conductor. If it is, and if you meet all the conditions outlined in the NEC, you can potentially use it as the grounding path. Secondly, consider the length of the conduit run. If you're relying on the FMC itself for grounding, make sure that the total length of the run between grounding points doesn't exceed 6 feet. If it does, you'll need to install a separate equipment grounding conductor. Thirdly, ensure proper installation and protection. Make sure that the conduit and fittings are properly installed and tightened, and that the conduit is protected from physical damage and corrosion. Given that the conduit is installed within a metal stud wall, it should be reasonably well protected from physical damage. Fourthly, comply with healthcare facility requirements. Be sure to comply with all applicable requirements for healthcare facilities, including those related to wiring methods, grounding, and the use of isolated power systems in critical care areas. Fifthly, pull an equipment grounding conductor. As a general practice, especially in healthcare facilities, it's recommended to pull a separate equipment grounding conductor inside the FMC, regardless of whether the conduit is listed for grounding. This provides an extra layer of protection and ensures a reliable grounding path, even if the conduit itself becomes damaged or corroded. Sixthly, verify compliance with 250.118. Ensure that the grounding path meets the requirements outlined in NEC section 250.118, which specifies the types of equipment grounding conductors that are permitted. Seventhly, regarding the 20 amp circuit, the size of the equipment grounding conductor must be appropriate for the rating of the overcurrent protection device protecting the circuit. Table 250.122 in the NEC provides guidance on the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. For a 20 amp circuit, a 12 American wire gauge copper equipment grounding conductor is typically sufficient. Eighthly, continuous support must be provided. Securely fasten the flexible metal conduit to the metal studs. Do not rely on the wall for support. Use approved fasteners such as straps, clamps, or hangers. Ensure that the conduit is properly supported to prevent strain on the connection. The support intervals must be in accordance with the NEC requirements for flexible metal conduit. Ninthly, be aware of ampacity darting. When multiple current-carrying conductors are installed in a single conduit, the ampacity of the conductors may need to be derated according to NEC Table 310.15 cone. If the number of current-carrying conductors in the conduit exceeds 3, the ampacity of each conductor must be reduced. Tenthly, examine the fittings used. Use fittings listed for grounding purposes to ensure a secure and reliable connection. The fittings should be designed to maintain electrical continuity between the conduit and the connected equipment. Make sure the fittings are properly tightened to prevent loosening over time. 11thly, document and label all circuits and conductors. Properly label the flexible metal conduit runs, circuits, and conductors in accordance with NEC requirements. This includes identifying the purpose of each circuit and the size and type of conductors. Accurate labeling helps with future maintenance and troubleshooting. In summary, while it may be permissible to use flexible metal conduit in a metal stud wall within a nursing home resident room on a 20-amp circuit, it's crucial to carefully consider all the applicable requirements and recommendations. This includes determining if the conduit is listed for grounding, complying with the 6-foot rule, ensuring proper installation and protection, complying with healthcare facility requirements, and pulling a separate equipment grounding conductor. By following these guidelines, you can help ensure a safe and reliable electrical system for the residents and staff of the nursing home. It's always advisable to consult with a qualified electrical professional to ensure that the installation meets all applicable codes and standards. If the FMC is not listed for grounding, a separate equipment grounding conductor must be pulled. In healthcare facilities, it is highly recommended to always pull an equipment grounding conductor for added safety. Verify that all connections are made up tightly using fittings designed for grounding to ensure a reliable electrical path. The conduit should be protected from physical damage and corrosion, especially in environments where these factors may be prevalent. Ensure compliance with NEC Article 517 for healthcare facilities, which provides additional requirements for electrical systems in patient care areas. Conduct a thorough inspection of the installation to ensure compliance with all applicable codes and standards. This includes checking the tightness of fittings, the condition of the conduit, and the integrity of the grounding connections. It is essential to properly size the equipment grounding conductor based on the overcurrent protection device rating as specified in NEC Table 250.122. Using the wrong size conductor can compromise the effectiveness of the grounding system. Consider using liquid-tight flexible metal conduit, or LFMC, for added protection against moisture and corrosion, especially in damp or wet locations. Provide adequate support for the flexible metal conduit to prevent strain on connections and ensure long-term reliability. Follow the manufacturer's instructions for installing and terminating the flexible metal conduit and fittings. Deviations from the instructions can compromise the integrity of the installation. When making connections to electrical boxes or equipment, ensure that the surfaces are clean and free from corrosion to provide a good electrical connection. Use antioxidant compounds on aluminum connections to prevent corrosion and ensure a reliable connection. Verify that the metal stud wall is properly grounded to provide a path for fault currents. The grounding of the metal stud wall should comply with NEC requirements. Document all aspects of the installation, including the type and size of the flexible metal conduit, the size of the equipment grounding conductor, and the location of grounding points. Keep the documentation for future reference and maintenance. It is crucial to address all these points carefully to ensure a safe and compliant installation of flexible metal conduit in a healthcare facility. Neglecting any of these requirements can lead to serious electrical hazards. It is best to err on the side of caution and follow best practices to protect patients, staff, and the facility itself. Remember to always consult the latest edition of the NEC and any applicable local codes and regulations before starting any electrical work. These codes and regulations are designed to ensure the safety and reliability of electrical systems, and they should be followed diligently. So to reiterate, the primary determining factor is whether the specific flexible metal conduit being used is listed for grounding purposes by a recognized testing laboratory. This listing indicates that the conduit has been tested and meets the requirements for use as an equipment grounding conductor. If the FMC is listed for grounding, there are specific conditions that must be met for it to be used as the equipment grounding conductor. These conditions typically include: firstly, the length of the conduit run must not exceed 6 feet. Secondly, the conduit must be terminated with fittings that are listed for grounding. Thirdly, the conduit and fittings must be installed in a manner that provides a continuous electrical path to ground. If the FMC is not listed for grounding, or if any of the conditions for using it as an equipment grounding conductor are not met, a separate equipment grounding conductor must be installed within the conduit. The equipment grounding conductor must be sized in accordance with NEC Table 250.122, based on the rating of the overcurrent protective device for the circuit. Even if the FMC is listed for grounding and the conditions for its use as the equipment grounding conductor are met, it is generally recommended to install a separate equipment grounding conductor within the conduit. This provides an additional layer of protection and ensures a reliable grounding path, especially in critical applications such as healthcare facilities. In healthcare facilities, there are additional requirements for electrical systems to ensure patient safety. These requirements are outlined in NEC Article 517. Article 517 includes specific provisions for grounding and bonding in patient care areas, which may affect the installation of flexible metal conduit. When installing electrical systems in healthcare facilities, it is essential to comply with all applicable requirements of Article 517, in addition to the general requirements for grounding and bonding in Article 250. The use of flexible metal conduit in metal stud walls introduces additional considerations for grounding and bonding. The metal studs themselves must be properly grounded and bonded to ensure a continuous electrical path to ground. The flexible metal conduit must be connected to the metal studs in a manner that provides a reliable electrical connection. This can be achieved through the use of grounding bushings or other approved methods. When installing flexible metal conduit in metal stud walls, it is important to ensure that the conduit is properly supported and protected from physical damage. The conduit should be securely fastened to the metal studs to prevent it from becoming loose or damaged. It should also be protected from sharp edges or other potential sources of damage. The decision to use flexible metal conduit in a healthcare facility should be based on a thorough assessment of the specific application and the applicable code requirements. Factors to consider include firstly, the location of the conduit run. Secondly, the type of equipment being served. Thirdly, the potential for physical damage. Fourthly, the presence of moisture or corrosive substances. In some cases, other wiring methods such as rigid metal conduit or electrical metallic tubing may be more appropriate than flexible metal conduit. It is always recommended to consult with a qualified electrical engineer or contractor to determine the most suitable wiring method for a given application. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. Failure to properly ground and bond electrical equipment can result in electrical shock hazards, equipment damage, and fire. It is important to follow all applicable code requirements and industry best practices when installing and maintaining electrical systems. Regular inspection and testing of electrical systems are also important to ensure that they are functioning properly and that all grounding and bonding connections are intact. In the specific case of using flexible metal conduit in a metal stud wall within a nursing home resident room on a 20-amp circuit, the following additional points should be considered. Firstly, the potential for moisture or humidity in the resident room. Secondly, the type of equipment being served by the circuit, such as lighting, receptacles, or medical equipment. Thirdly, the need for flexibility in the wiring system to accommodate future changes or renovations. Fourthly, the importance of minimizing noise and electromagnetic interference in the resident room. Based on these considerations, a decision can be made as to whether flexible metal conduit is the most appropriate wiring method for the application. If flexible metal conduit is selected, it must be installed in accordance with all applicable code requirements and industry best practices to ensure a safe and reliable electrical system. Remember to consider the specific environment of the nursing home, focusing on the comfort and safety of the residents. This includes factors such as potential exposure to cleaning chemicals, the need for easy maintenance, and the importance of minimizing disruptions to the residents' daily routines. By taking these factors into account, you can ensure that the electrical system is not only safe and reliable, but also well suited to the specific needs of the nursing home environment. Before beginning any electrical work, it is essential to obtain the necessary permits and approvals from the local authorities. This ensures that the work is performed in compliance with all applicable codes and regulations and that it is subject to inspection by qualified inspectors. Failing to obtain the necessary permits and approvals can result in costly delays, fines, and even legal action. It is also important to ensure that all workers involved in the electrical installation are properly trained and qualified to perform the work safely and effectively. Electrical work can be dangerous, and it is essential to have the knowledge and skills necessary to avoid electrical shock, arc flash, and other hazards. By following these guidelines, you can help ensure that the electrical installation is performed safely, efficiently, and in compliance with all applicable codes and regulations. This will help to protect the residents, staff, and visitors of the nursing home from electrical hazards and ensure the long-term reliability of the electrical system. When using electrical equipment in a healthcare setting, it's imperative to select devices that are specifically designed and listed for healthcare applications. These devices often have enhanced safety features and are constructed to withstand the rigors of the healthcare environment. Additionally, ensure that all electrical equipment is properly maintained and inspected regularly to identify and address any potential safety hazards. Implement a comprehensive electrical safety program that includes regular training for staff on electrical safety procedures, proper use of electrical equipment, and emergency response protocols. This program should also include regular inspections of electrical systems and equipment to identify and correct any potential hazards. Develop and implement an emergency action plan to address electrical emergencies such as power outages, electrical fires, and electrical shock incidents. This plan should include procedures for safely shutting down electrical equipment, evacuating affected areas, and providing first aid to injured individuals. Consider implementing an isolated power system in critical care areas such as operating rooms and intensive care unit. Isolated power systems provide an additional layer of protection against electrical shock hazards by isolating the electrical supply from ground. This can significantly reduce the risk of electrical shock to patients and staff in these critical areas. Ensure that all electrical outlets and receptacles are properly grounded and that ground fault circuit interrupters, or GFCIs, are installed in areas where there is a high risk of electric shock, such as bathrooms and near sinks. GFCIs can quickly detect ground faults and shut off the power to prevent electrical shock incidents. When using extension cords, be sure to use heavy-duty cords that are properly rated for the intended use. Avoid overloading extension cords and do not run them under carpets or rugs, where they can be damaged or create a tripping hazard. Regularly inspect extension cords for damage and replace them if they are frayed, cracked, or otherwise damaged. Ensure that all electrical panels and enclosures are properly labeled to identify the circuits and equipment they serve. This will help to prevent confusion and errors when performing maintenance or repairs. Keep electrical panels and enclosures clear of obstructions and ensure that they are easily accessible in case of an emergency. Avoid using portable heaters or other high-wattage appliances in resident rooms, as these can overload circuits and create a fire hazard. If portable heaters are necessary, be sure to use models that have been tested and listed by a recognized testing laboratory and that have built-in safety features, such as tip-over protection. Prohibit the use of unapproved electrical devices or modifications to electrical equipment. All electrical work should be performed by qualified electricians who are familiar with the applicable codes and standards. Implement a lockout-tagout program to ensure that electrical equipment is de-energized and rendered safe before performing any maintenance or repairs. This program should include procedures for identifying and isolating energy sources, locking out equipment, and verifying that the equipment is de-energized before work begins. Establish a system for tracking and managing electrical safety incidents, such as electrical shocks, arc flash incidents, and equipment failures. This system should include procedures for investigating incidents, identifying root causes, and implementing corrective actions to prevent future incidents. Regularly review and update the electrical safety program to ensure that it remains effective and reflects current best practices. The electrical safety program should be a living document that is continuously improved to meet the evolving needs of the healthcare facility. Electrical safety in healthcare facilities is a shared responsibility. It is important for everyone to be aware of the potential hazards and to follow the established safety procedures. By working together, we can create a safe and reliable electrical environment for patients, staff, and visitors.